We talked about circuits containing capacitors when we talked about electric fields and how capacitors can store energy in a circuit. We talked about circuits that contain resistors. Now let's combine the two for a simple DC circuit. So we're going to look at DC circuits or direct current circuits containing both resistor and a capacitor, often referred to as an RC circuit. Again, resistors are represented by a capital R. Capacitors are usually represented by a capital C. So an RC circuit is one with a resistor and a capacitor in it. So I have a battery attached to a resistor and a capacitor, and I have a simple switch here. When I close this switch, the capacitor will begin to charge. Current will begin to flow in this circuit. But what will happen, of course, is the capacitor, once it's fully charged, won't let current flow through the circuit anymore. This circuit will stop, current will stop flowing once this capacitor is completely charged. Right now, the potential across this capacitor is zero. There's no charge on one plate, there's no charge on the other plate, or no net charge, so the potential across the plates is zero. If we look at Kirchhoff's loop rule, and we add and subtract the voltage changes as we go around a loop, let's start in this corner and go around this way. We cross the battery, so we add the battery's potential. Switch doesn't do anything, it's just a wire. Here we're going to go in the direction of the current, so the current will be downward here, current I. So we subtract the voltage drop across the resistor, I times R. Here we go across the capacitor, we subtract the voltage drop across the capacitor. But how do we know what the voltage is across the capacitor? Well, remember the equation for capacitance is the charge on a capacitor is equal to the capacitance times the voltage. Solving this for voltage, we get voltage is equal to charge over capacitance. So I'm going to subtract charge over capacitance. This is an interesting equation because it contains the charge, Q, and the current, which is how the charge is changing with time. So rewriting this, the current, right? The current is change in charge with time. So this contains both the change in charge with time and the charge. There's a specific type of an equation that deals with these forms. It's called a differential equation. You might have heard in math classes differential equations. Some of you might have had differential equations or are currently in differential equations. It's typically a class you take after Calc 2 or Calc 3. You do not need to know differential equations for this class. The only expectation is algebra and some trigonometry. You don't even need to know calculus. So I'm just going to give you the answer to this problem. If you look at with time, since it's changing with time, the potential across the capacitor, you get a plot that looks like this one in blue, where at time 0, the potential is 0, and as time increases, the potential increases up to the potential across the battery. So this is a timing circuit, basically. It takes a little while for the capacitor to charge. Think of it like filling up a bathtub, right? How quickly you fill up the bathtub depends on two things. How big is the bathtub, or how big is the capacitance of a capacitor, and how quickly the current, how quickly the water flows into the bathtub, which is the current here in this circuit. You can control the current by changing the resistance. A bigger resistance means the current slows to a trickle. A bigger capacitor means that you have a bigger capacitance to fill. So there's a thing called a time constant, tau. This is the Greek letter tau, representing time constant, which is R times C. R is the resistance value of the resistor, C is the capacitance of the capacitor. The bigger tau is, the slower your capacitor charges. So by changing R or changing C, you can change how quickly, or both, you can change how quickly the capacitor charges up. So the voltage across a charging capacitor, is given by this equation here. The potential across the capacitor is equal to the potential across the battery times the product here, 1 minus e to the minus t over RC. This e is the opposite of the natural log in your calculator. Usually in your calculator, you'll see it as a little, like an e to the x button. So it does not represent, this is not a variable, this is a function in your calculator. So if you know the time t, you know the resistance value R, you know the capacitance C, you can calculate for any time t what the voltage is across the capacitor. For a charging capacitor, at time t of 0, the voltage better be 0, right? If you are just about to start charging the capacitor shouldn't have any voltage across it. So at time t0, this is e to the minus 0 or e to the 0. Anything raised to the 0 power is 1. 1 minus 1 is 0. 0 times the EMF is 0, so the voltage is 0. At some hugely later time, when time is approaching infinity, this capacitor should be fully charged. It should have a potential of E across it, right? The potential, whatever the potential of the battery is. Well, let's look at that. E to the minus infinity is 0. 1 minus 0 is 1. 1 times the EMF of the battery is the EMF of the battery. So that works out. So this is the equation in green here for a charging capacitor. What if you have a capacitor that's charged and you want to discharge it? Same thing. Again, instead of filling up the bathtub, now you're draining the bathtub. How long does it take to drain the bathtub? How long does it take to drain the charge from a capacitor? Depends on how big the capacitor is, and depends on how much resistance you have to the flow of electricity leaving the capacitor. The equation for a discharging capacitor is slightly different. You'll notice the 1 minus term is gone. It's the EMF of the battery times e to the minus t over RC. So again, if you know what the EMF of the battery is, you know the resistance of the battery, you know the resistance of the resistor in the circuit, the capacitance of the capacitor. You can calculate the potential across the capacitor for any time t. But why do we care about these types of circuits? Well, since it takes a while for a circuit to charge up or discharge, these can be used as timing circuits, and that's their popular use. Your book goes into a little more detail than I will here, so be sure, of course, to read your book. But an example would be windshield washers. Most of you have variable speed windshield washers. It's pretty typical now in your car, if you have a car, right? You have that little dial where you can turn. Variable speed might even be off, medium, and high, or low, medium, and high. Or you'll have a little knob where you can just adjust, fine-tune it, and change when the windshield wipers move from either a big delay to no delay. What you're effectively doing when you spin that little dial in your car is you're changing the resistance value of the circuit, making it bigger or smaller. The smaller the resistance value, the more rapidly the trigger will occur, the more rapidly your windshield wipers will move. The larger the resistance value, the more slowly it will be triggered, and the bigger the time between events when your windshield wiper moves across the screen. So there are a lot of these types of triggers. Any type of flashing light, if you've ever seen a flashing LED, it's almost certainly this type of a simple timing circuit. So these simple circuits are very useful, and we will actually be doing a lab on RC circuits, most likely, so we can look at how these RC circuits work in lab.